Welcome to Dr. Jimmy's Applied Calculus. We're starting Chapter 6, More Things Involving Derivatives, and that definition and what it leads us to. And so Section 6.1, Product Rule for Derivatives. Now, with functions, if we have more than one, we typically do basic arithmetic operations. We might add them. Along with that, maybe subtract. We might multiply things. So these two basic operations we've dealt with as far as the derivative. That the derivative of a sum or separate terms is the same as the sum of the derivatives. Okay. A very straightforward distributing derivative through a sum. And we also found that the derivative of a constant multiplied by a function is the constant times the derivative of the function. So in both of these settings, very straightforward. We almost would do it naturally without thinking. So no changes, direct. But other operations that we might do with functions might not work out quite as simple. So instead of a product of a constant and a function, what happens if we take a product and then look at its derivative? So, a big caution that very basic idea that we might want to use to distribute it through the product doesn't work. So, it's not the product of derivatives. So, first thing to get used to. We had the nice thing with the sum, but that's not going to work with the product. So we won't take derivative of f times derivative of g. It just doesn't work. So big caution. Caution, caution. Not the product of derivatives. So we're going to do, well, let's look at this from the definition. So let's take the derivative of a product of two functions, f of x and g of x. That would be, from the definition, limit as the change in x, or here I call it h, goes to 0. So that over that h, and then they would have this expression, the product of the two, evaluated at some x, and then add on the change to get the new height of the function. So change in y over change in x, take the limit as h goes to 0. So I have f of x plus h, g of x plus h, minus Oops, I see I left out a letter in there, g of x. F of x plus h, g of x plus h, minus f of x plus h, g of x. Whoa, something wrong. Oh, miscopied. That should be g of x plus h. Oh, I can fix that by, let's see, I don't want that there, so let's get rid of it. So this mistake I've canceled out by putting a plus instead of a minus. So now I would be back there. Should be that. So fix my mistake. Same thing. Oh, well, it's interesting that if I factor from the first two terms now after the mistake, divided by h. This looks like the definition of the derivative of g. And the other, if I factor out g of x, what's left would be f of x plus h minus f of x, everything, all these things over h. So now if I look at this limit, f of x plus h, if h goes to 0, that's just going to be f of x. The difference in g over h, oh, that's just the derivative of g. And in the next thing, g of x not affected by h, so it becomes g of x, and the other part is the derivative of f. So now we have this product rule. So we started with the derivative of the product. We ended up with this expression. So derivative of the product of two expressions turned out to be, well, we do get a derivative of an expression, but only one of them. So leaving one undisturbed, differentiate the other. And there are two ways to do that. So we can take the first function times the derivative of the second, and then we can take this second one in the list times the derivative of the first one. So we get a two terms of products with derivatives, but only one derivative at a time. So different than if we just had one term with two derivatives. So this is our product rule. So right now, a basic example, if we took y equal 3 to the x times the polynomial 4x squared plus 3x minus 2, I could look at that. Certainly, it's written that way as a product of some expression f of x and g of x. So if f of x is the 3 to the x, its derivative, since that's an exponential, would be the exponential, but then augmented with the natural log of the base. And the derivative of the g would have been 8x for the first term, and then derivative of 3x plus 3, and then the minus 2 goes off to 0. So those are the two parts. So the derivative of y would be one of those, 3 to the x, times the derivative of the other, g prime, plus then g, the other function, and times the derivative of the first function, 3x natural log of 3. Okay, venture into another example. 4x cubed plus 3x squared minus 2x plus 6 multiplied by another factor of 5x to the fourth plus 7x cubed plus 8x minus 2x plus 1. Let's see, fix that up a little bit. So what's the derivative? Well, one way to be, we could multiply this out, collect like terms, and take the derivative. That might be a little tedious. Or we could treat it as a product, find the derivative, which would be one of those factors without derivatives. So we'll take this first one, 4x cubed plus 3x squared minus 2x plus 6 times the derivative of the second factor, so 20x cubed, and then we would get 21x squared. Oops, get an x in there. Plus 8. Oops, sorry, let me do a little, I don't know what I said or what I erased. This originally should have been 8x squared, so that would make it 16x, derivative of the next term minus 2, and then a 0. And that's just part of it, because now I need this second function, 5x to the fourth plus 7x cubed plus 8x squared minus 2x plus 1, and the derivative of the first factor, 12x squared plus 6x minus 2. And so I have the derivative without the tedious work of multiplying out. Now at this point, I may need to do that for the derivative, but there may be less things to collect. But at least finding some form of the derivative is much quicker using the product rule.